Hi everyone, and welcome to this presentation. My name is Francesco Sinigaglia. I'm a graduate student jointly at the Instituto de Astrofísica de Canarias in Tenerife, in Spain, and the University of Padua in Italy. And today, on behalf of myself, Francisco Shukitaura, Kentaro Nagamine, Yuri Oku, and Andres Balaguer-Antolínez, I'm here to briefly review and summarize our recent effort on trying to fast and accurate modeling the Lyman-α forest for current and forthcoming surveys. Just a disclaimer, most of this work is presented in this paper you can already find on the archive and which has been submitted to the Astronomy and Astrophysics Journal. All right, so without further ado, let me present the outline and motivation behind this work. So current and forthcoming surveys need accurate Lyman-α forest modeling at the field level to produce mocks, to validate pipelines, and to test systematics. And a very difficult task is to perform it at a coarse resolutions in order to produce very fast, large volume mock light gauge generations covering the full sky, for instance. There has been several efforts to do it and presented in the literature over the last years, some analytical, calibrated, and machine learning with a special mention to deep learning methods achieving very good results. But in this work, we wanted to take a step back and try to exploit as much as we can in the light of our recent knowledge. We have acquired some analytical tools which are already there in the literature. So, and in particular, we wanted to expand and improve upon a widely used analytical approximation, which is the so-called fluctuating Gunn-Peterson approximation that we will have a look at in the following slides. Anticipation, one of the main contributions of our work is to introduce further terms in the analytical modeling, accounting for non-local bias, and in particular, we feed the free parameters of our model using as reference a cosmological hydrodynamical simulation that I will also introduce in a few slides. And in order to assess the performance of our method, we test the predictive summary statistics, comparing that to the reference simulation. Good. So to make sure we are all on the same page, what is the Lyman-α forest? So the Lyman-α forest is essentially an ensemble of thick set of absorption lines that appear in the quasar spectra as a result of the quasar light rays being intercepted by intervening H1 clouds along the line of sight. So essentially the physical mechanism that determines the arise of the Lyman-α forest is the light emitted by quasars indeed impact on H1 clouds intervening along the line of sight. And when this happens, there is a certain probability that the Lyman-α forest transition and absorption occurs, which at rest frame wavelength is at 1,214 angstroms. But because the universe is expanding, this will be in the observed spectra will appear at different wavelengths depending on redshift. So the result is that due to just one transition, we are going to see several absorption lines in the observed spectra, like it is depicted by this cartoon. And as a result, the Lyman-α forest efficiently traces the matter distribution. And what is very, very important and very, very interesting is that this happens at high redshift. So typically a redshift larger than 1.8. The reason being that if we observe the Lyman-α forest from Earth, then we are limited by the opacity of the Earth atmosphere. So which is opaque to the UV transition. But this is very interesting because this is a regime which is poorly traced by galaxy clustering. Good. So, and before proceeding with the main modeling we perform in our paper, since I have talked about our contribution in non-local bias, then let me first expose how we do it. So there are several ways to capture non-local bias. What we do is the following. So we first compute the gravitational tidal field tensor, which is this guy here. So essentially one computes the second derivatives and the Hessian matrix delta I, delta J of phi, which is the gravitational potential in Euler coordinates R. And once one computes the eigenvalues, lambda 1, lambda 2, and lambda 3, Han and collaborators in 2007 proposed this classification of the 4 types of the cosmic web into knots, filaments, sheets, and voids, depending on the relative signature of the eigenvalues. So all positive eigenvalues is a knot, all negative is a void, and then there are intermediate situations, which are filaments and sheets. Just to give you a flavor of what is the occurrence of these cosmic web types in a simulations, I have reported here a table, also presented in our paper, where I essentially computed the volume filling factor in a simulation in a real space and redshift space, where we can see that, as expected, knots are more rare, whereas filaments, sheets, and voids have a larger occurrence. Okay, so why this is a quantitative but phenomenological cosmic web classification, which we can directly relate it to a more, let's say, formalistic Eulerian bias, perturbative bias expansion, like the ones presented in the paper by McDonald and Roy 2007 and following works. And following the work by Kitaura and collaborators published last year in 2022, what we can do is to build these 3 objects here, these 3 guys, the 3 main invariants of the tidal field tensor, which are built this way. So it's essentially the trace, the sum of the cross products, and the determinants. And these 3 have been shown in this paper to model a perturbative bias expansion, including all the non-local dependencies up to the 3rd order. And once we know it, we can, on the other hand, relate it to the phenomenological cosmic web classification in this way. So I don't want to enter into too many details here, but I leave you here the slide and you can have a look at that. So the take-away message of this slide is that on one hand, we perform cosmic web classification, but on the other hand, this is not just phenomenological, but has physical dependencies behind, which essentially goes up to the 3rd order in perturbative bias expansions because of these arguments here. So essentially, by taking into account the cosmic web classification, as I will show in the next few slides, we are effectively modeling the non-local bias up to 3rd order. Good. So the FTPA, the fluctuating gap Peterson approximation, is an approximation to model the intergalactic medium at high redshift, which arises because one observes a tight relation between the temperature and the matter density and the gas density. But after some algebra and after assuming, which is usually a good assumption with some tweaks, that we can substitute the gas density for the dark matter density and vice versa. Essentially, one can write the fluctuating gap Peterson approximation here after FTPA as follows. So essentially, one can express the optical depth for the Lyman-α Forest tau as a power law of the dark matter density with 2 free parameters, A and alpha, which needs to be tuned on a simulation. And also, we want to perform our analysis in redshift space. So this is why we map particles from real Eulerian coordinates R, I is the subscript indicating particle by particle, to redshift space, as by also taking into account the velocity bias factor, which is a free parameter in our model as well. Okay, and the final, I promise, is the final model slide. What is the contribution of our paper? So what do? We try to go beyond the FTPA. And what we do is the following. So we first add 2 terms expressed in these 2 exponentials here, which are a boosting and a damping terms, controlled by these 2 scale parameters, delta star 1 and delta star 2, which essentially when delta is much smaller than these scale parameters, this goes to 0. But when delta becomes comparable or larger than these 2, acquire importance. One has a minus sign and one a plus sign, so these 2 have contrasting effect, and this is in fact, one is a boosting and the other is a damping or cutoff terms. And second, we don't want this relation to hold universally over the whole volume, because over the cosmic web, we know that there is different physics going on. So we wanted to allow this model to be cosmic web dependent. And the easiest way to do it is to assume that this set of 3 parameters, which is now made of, A, alpha, delta star 1, and delta star 2, can depend on the cosmic web. So we fit separately these 4 coefficients depending on the cosmic web type. So we no longer have 4, but now 16 free parameters. And finally, eventually, since we eventually see that we were lacking some small-scale structures, especially in voids in the underdense environments, then we artificially sample it by adding a stochastic noise term to model the small-scale power. And this stochastic noise term, which is only added in voids, because we don't need it in the other cosmic web types, is randomly sampled from a negative binomial distribution, which has very interesting statistical properties. Again, I don't want to enter into too many details here, but I encourage you to read the discussion we have in our paper and also to refer to the one of Peebles, 1980. Okay, so once we have this model, we feed our parameters by an MCMC efficient scheme, having this as likelihood. So I point your attention to 2 things. We don't fit cell by cell the flux values, first of all, but we take as chi-square here in the likelihood just the difference between the 1-point PDF. Second, we do it cosmic web type by cosmic web type. This is the way we fit the coefficient. This is done in order not to have a huge degeneracy between all the parameters and to make the MCMC scheme faster and more efficient. Good, so it's now the right time to briefly present our reference simulation. So it's a 500 megaparsecs over H box size simulations with 1024 cube particles, which is run with a particle mesh n-body code, which is inherited by the gadget code. It includes a detailed galaxy formation physics modeling, and now, even though we in principle have a much higher resolution, we explicitly work at a coarse 2 megaparsec over H cell size mesh resolution. And this is done, again, let me stress the point, this is done on purpose in order to have a model which can work on a coarse resolution very well in order to be able to cover very large volumes in an efficient way. So the first qualitative comparison we can do is to address the visual resemblance of a slice through our simulation box here on the right to the hydrodynamic simulations. We see by eye it's not perfect, of course, but it has a very good visual resemblance. I didn't show here the FTPA. You can have a look at that in our paper, but it doesn't look as similar as our model to the hydrodynamic simulation. Then we have here the 1 and 2 point statistics, so the power spectrum, the PDF, and the cross correlation. Here on the left is in fact the 1 point PDF, the probability distribution function. Here we plot with the red solid line our reference simulation, and with other color lines and line style lines other models. I don't want to again to review all these models, which are the one which we test in the paper, but let us stick to the starting model. Let's say the FTPA, the standard one, which is the yellowish line, and the final one, our workhorse method, which is the blue line method here. So what we see is that while the FTPA, for instance, fails to reproduce this peak at high flux, which corresponds to the low density environment, our model capture much more accurately the 2 peaks, and it's not perfect here in the central regime, but also notice that the Y scale here is in log scale. If we plotted that in linear scale, we wouldn't see such a huge difference. Here on the right, in the upper panel, you see the ratio between the predicted and the reference power spectra. Again, let's just compare the yellow and the blue one. Ratio 1 means that we are perfectly reproducing the reference simulation. You can see that the yellow line drops quite fast, whereas the blue line is within a plus or minus 5% deviation from the reference up to K 1.5, so which is fairly good, a pretty good achievement. And here on the bottom panel in the right figure here, we are seeing the cross correlation coefficient with the reference flux field from the simulation, which again we assume as ground truth. And again, if we compare the yellowish line with the blue line, we see that, for instance, at k equal to 0.5, our model is around 80% cross correlation, and the FTPA is around 50 something, let's say 55%. So there is a gain by about 25 to 30% from the FTPA to our model. And eventually, here we also looked at the reduced pi spectrum, which is the 3-point statistics in Fourier space. We looked at these 4 triangular configurations from K1, K equal to 0.1, K 0.2, to much smaller scale configuration, which is K1 equal to K2 equal to 0.5. And we see that in all these cases, again, taking the yellowish line as the FTPA and the blue one as our reference, as our workhorse model, then we see that in all the cases, the blue lines models much better the reference statistics. And a very interesting and curious thing is that if we look at these pronounced features, our model capture these features much better than done by the other models. And coming to the conclusions, this is a summary and conclusions. So we have devised indeed a method to predict the Lyman-α forest expanding upon the FTPA, which was our primary goal. And we have explicitly modeled non-local bias and damping and acoustic terms, which we regard as our main contributions of this work. We have addressed the summary statistics, and we have seen, by comparing summary statistics to the reference simulation, we have seen that our model outperforms the standard FTPA. And we are currently using this model to study BAO predictions to come soon, so stay tuned. And eventually, we want to highlight that our model can be used to generate fast mock Lyman-α forest light cones. It can be used to perform reconstruction, and it can be used, in fact, as we are doing, to quickly simulate the Lyman-α forest to study 3D correlations. With this, I conclude. I thank you very much for your attention, and I thank the organizers of Cosmology from Home to letting me the opportunity to present our work.